Well, bam. Number 6. Here's where things get interesting. So I'm going to start this the same way that I've been doing it. Domain is on my x-axis. I look and I see -9, I got nothing. -8, I got nothing. First thing I see here is the -4, right? But then I need to look to see the next x value that has a value, has a coordinate on it, right? Well, I've got this solid line. Even though there's not a point until way over here, this solid line right here implies that there are hundreds upon hundreds upon hundreds of tiny little dots all stacked up here, right? So technically there is a coordinate right here on -3.999. And there's another coordinate right here on -3.8. Another coordinate on -3.567893124 repeating. So I could start listing them, right? Like this. But technically, I'm not ever going to be able to list all of them, and it would take me for the rest of time to try to do that. So instead of listing them, I'm going to use a compound inequality. I know that all the x values in between the -4 all the way to the 8 are going to be used for this graph. Notice that there's nothing after the 8, just kind of stops there. The rules for the inequality symbols are the exact same as they are when we're graphing them on a number line. This closed circle on the end means that I have less than or equal to, and this open circle on the end means that I just have less than. So now the range is the exact same process. I'm still going to do bottom to top. Let me highlight my graph here. Starting at the bottom. Nothing happening. The first thing I see that's being used is the -2. It has the graph going through it right here, as well as an open circle over here on the end. This point right here that's going through -2 is using the -2 as its coordinate. If I was to write the coordinate out, it'd be 0, -2. So I have to include -2 in my range. But then I notice again, if I were to zoom in really, really close, I would have an infinite number of points all along this line. So the next number, if I was to make a list, would be like -1.99999 repeating. And then it'd be -1.99999 again with one less 9. And that would take me a billion years. So instead, I'm just going to write the inequality to show that any y in between -2 and +2 up here is included in my range. Also, you don't need the little squiggly brackets anymore. Once you have your compound inequality, you can just leave them without the brackets at the end. Sometimes you'll still see them, but you don't need them at that point. So, while we're on the topic of comparing these different types, a little piece of vocabulary. Discrete graphs are made up of disconnected coordinates. Those are just the points. We've talked about that before. And then continuous graphs are the connected lines and curves. So as long as you see a line, whether it's curved or straight, that's called continuous, and then the scatter plots are called discrete. So, just a few more. Number 7. Again, domain is still going to be from left to right. So, looking at my x-axis, I got nothing. First number I see is -3. Going across, it ends here at 6. So, notice again, they both were closed circles. So, I've got less than or equal to, less than or equal to. Okay? Now, range, bottom to top. Looking at my y-axis, got nothing. First point I see here is at the -4. It goes all the way up to +5. Also, I didn't really mention this before, but notice my range has a y in the middle. Domain has the x, because those are the values that we're looking at, right? Okay, number 8, same thing. Domain is from left to right, so I'm starting over here on the left. I'm moving across. First number I see here is a -6. Closed circle. Going across. 7 is the last number I use. Open circle, so I don't put a line underneath it. Okay, range. Starting at the bottom of the graph down here, moving up. First number that's used is this -8. It's an open circle over here. Going up, going up. While yes, there's a point on -5, there's still points on all these up here, right? There's points, little thousands, billions of little points here. And the last one is at that +4. Okay. Number 9, here's something that's a little bit different. When I look at my x-axis and I try to look to see, starting at the left, what numbers are being used, I notice that this has an arrow at the end. That means that it's going to go on forever. And really, basing it on the pattern that we already see, this is going to go outward forever. Even though it's going outward pretty slowly, it is going outward to the left forever. So that means the number that's furthest to the left that this domain is going to reach is actually -infinity. You've heard of infinity before, but negative infinity implies that you are going to count forever in the negative direction. So negative infinity is the farthest to the left that this graph is going to go. Okay. Now it is continuous, so there's thousands of little points in between here, so I'm going to keep going to my right, and I see that it goes to the right forever, which means the last value of my domain is to infinity, this time positive infinity. Okay. Notice that there's no lines underneath my inequality symbols. That's because infinity is an idea. You can't be equal to infinity, right? It's kind of like a Chuck Norris joke waiting to happen. You can't be equal to something like that. Now, what this implies, negative infinity all the way to positive infinity, that really implies all the numbers, right? What number is not in between negative infinity and positive infinity? So another way that you could write this is by saying that the domain is simply all the real numbers, right? Now, this is slightly different from all real solutions because we're not trying to solve anything. We're trying to make a list of numbers, and we're saying that, hey, all the real numbers would be included in this domain. So going back up to the top of my notes, there's a fancy symbol, looks like this, that we can use to denote all real numbers. Okay, I'm going to write it again slowly. You draw one bar, you draw the next bar right next to each other, and then you make your R across the top of it both. That's the symbol that stands for all real numbers. I call it the fancy R. So what I could have done here for the domain is just drawn a big old fancy R and called it a day. And I'll show you that here in a second. So now, got to finish out with the range, starting at the bottom, right? Well, I've got these arrows that show that it goes down forever. So again, negative infinity. Then I'm going up my y-axis, and it stops here at the 4. So it doesn't go up to positive infinity, but it does go down to negative infinity. Okay? So number 10, domain is from left to right. So I'm starting over here on the left side of my graph, except that I see this arrow. So I know it's going to go forever to the left, negative infinity. It's got an arrow on the top as well, means it's going to go forever to the right, infinity. Or I could just put a big old fancy R and call it a day. Okay, so range, bottom to top, starting here at the bottom, looking upwards. Well, again, these arrows mean it's going to go down forever and up forever, so I could just put a big old fancy R to show that it's literally all the real numbers. Okay, number 11, we have a discrete graph. So again, starting on the left-hand side of my graph, and I read across, the first number I come to is this -4. I'm not going to do inequality symbols because there's not 1,000 trillion billion gajillion points in between here and here. So the next one really is just -2, then 0, then 2, then 4. I go back to my squiggly brackets because it's just a list. The range, starting at the bottom, going up, -2, -1, +2. Number 12. Again, domains from left to right. I'm starting over here, going across. First number I see is -2. This is a continuous graph. So I'm going to use my inequality symbols. Last number is a 3. Range, starting at the bottom of my graph and going up. First number I see is -6. And literally -6 is the only number that's being used. No other number would be a part of this graph's range. Almost done. What is the domain and range of the list below? Again, domain is the list of x values, so it needs to include the numbers I've circled here. So obviously A is out. B has the right numbers, 11, 6, 2, and 18, but so does D, right? So we got to look at the range. The range needs to include -3, -2, 0, 2, 4, meaning it has to be D because it's got that 0 that it needs. Number 14, what's the domain of the table? Well, again, domain just means the x's, so I just need to list these puppies out. You want to do them from least to greatest. What is the range of the mapping? Well, range means y's, so I just need to list this side out. Okay, domain and range of this equation. Well, this is just a linear equation. In fact, I'm pretty sure this is similar to the equation that was in the parent functions lesson from topic 1. It's just a linear equation. It's going to look something like this when you graph it. So that means it's going to go forever to the left, forever to the right, forever up, forever down. So the domain, all real numbers. The range, all real numbers. Okay. 17 is very similar. It says, what is the domain and range of the two parent functions? Well, this is the linear parent function. And we know what she looks like, right? Goes through the origin, forever up and to the right, forever down to the left. So again, domain, all real numbers. Range, all real numbers. Okay, this is the quadratic parent function, which we've learned about, and we know what that one looks like as well. It's a parabola that's concave up, goes through the origin. So the domain here, well, it goes forever to the left and forever to the right, so it's all real numbers. And the range, bottom to top, starts here at 0 and then just goes up. So from 0 to infinity. All right, I know I sped up there at the end, but I wanted to make sure this video wasn't like 45 minutes long. So if you have any questions, please do not hesitate to stop by the Tutoring Hub and talk to any of the algebra teachers or any math teacher really about domain and range. It's a very important topic that you understand. It comes up a lot, and it's really a good thing to